Hello and welcome to this recorded training course on the coursework unit for Edexcel A2 Physics, Unit 6PH06. Following a brief introduction to the structure of the unit, we will be looking at the assessment criteria in detail and then seeing how they are applied to two real scripts. As we go through the course, we will deal with some of the key issues as they arise. The task on which the students are assessed is introduced by a briefing document, which we will say more about in a moment, and the task consists of 3 sections. The task should be unknown to the students before they start. In addition to the briefing document, they are given a copy of the criteria. They are to work under examination conditions, except that there are no time constraints. The work is usually completed in about 3 hours and will spread over several lessons. Each candidate works by themselves for the whole assessment, and their work must be retained by the supervisor each time they stop work. There is an option for you to do the marking, Route 1A, and you will send a sample of your scripts to be moderated. Or you can choose Route 1B, in which all the scripts are sent to Edexcel for examiners to mark. Your examination officer must make the appropriate selection when the candidates are entered. There is a guidance document available, and we refer to that at the end. There is 1 mark for each of the 40 criteria, so the important thing is for the candidates to fulfill each criterion, and they must do so at a level sufficient for the award at A2 and show some progression from AS. The criteria vary in difficulty. They do not all have the same demand. The document called Notes on Assessment Criteria gives amplification of the sort of thing expected to fulfill the criteria at this level, and this is available from the website. Before we look at the criteria individually, we will look at the subgroups into which they can be divided, as this makes them easier to consider. P1 to 3 should be complete enough so that a lab technician could put out the apparatus and set it up with no further instructions. P4 to 7 refer to 2 of the measuring instruments, so P6 and 7 are repeats of P4 and 5. P8 to 10 refer to the actual readings. P11 to 13 concern the overall experiment and look ahead to carrying out the experiment. P14 to 16 are marks for clarity of expression and refer to the plan only. The M marks concern the readings taken and do not apply to any data used in the analysis section. There are 4 analysis marks for graph work and a further 4 for using the graph. A9 to 11 concerns some technical aspects of the report. A12 to 14 cover uncertainties, and A15 to 18 are about drawing conclusions and evaluating. So, on to the planning criteria. For P1 and 2, candidates list the apparatus and give details, as full as possible, and they need to estimate values where necessary. P3 is for a diagram that shows clearly how the apparatus is used in taking measurements, so that another experimenter could use it to set up the apparatus correctly. It is not necessary to draw a stop clock or a balance, as these are not used in changing the variables. The diagram should have dimension lines to show physical size or distances, where relevant. The lines should indicate the point to which the measurement is made. For example, the filament of a bulb rather than the glass envelope. Above all, the diagram should be to a standard that might be expected of an A-level physicist. P4 and 6 are easy marks and given for stating which instrument will be used to measure what variable. Nevertheless, this should be clearly stated and not left for the marker to work out for themselves. P5 and 7 are for calculating the percentage uncertainty introduced by using that instrument. This is usually given by the instrument's precision divided by a typical reading. This will need to be estimated by the candidate. P8 candidates should describe any techniques they will employ to improve the accuracy of their measurements. For example, timing 10 oscillations, or pausing to allow components to reach the same temperature. P9 is for controlling variables to ensure that separate readings are comparable. For example, ensuring that each set of oscillations has the same initial amplitude. P10 is for discussing whether repeat readings are appropriate. Sometimes the method, such as timing a capacitor discharge, makes it difficult to repeat distinct readings, and repeating the whole experiment becomes an option. Identifying anomalies to exclude them from means is the usual justification. P11 candidates are expected to consider the safety of their apparatus and themselves, and should identify a hazard and give a precaution. Declaring there is no hazard is an option, but should be justified. P12 is for showing how the data can be used to determine the outcome described on the briefing, not just which graph to plot. P13 is for considering likely sources of error, or what will be difficult to determine accurately. This requires some careful thought and will call for prior experience of practical apparatus and methods. P14 and 15 are for spelling, punctuation and grammar, when considering technical terms only, and they should be awarded as long as the meaning is clear. P16 is for writing a clear plan. Candidates should say, at least, that they will vary this and measure that. A surprising number of candidates forget to say anything like this. The implementation and measuring phase. For M1, the reading should be exactly what is shown on the measuring instrument. The precision is as discussed in P5 or P7, and the readings should be to the same precision. For M2, the table should contain the uncertainty in each variable, expressed as a number, and for M3, a unit should be quoted for each of the measured values. Derived quantities are considered in the analysis. For M4, reference should be made to the plan, and if no change was thought necessary, some explanation should be made. This would usually be because the readings follow the pattern expected and repeats were concordant. For M5 and 6, there should be enough readings to show properly the behavior of the system, but not so many that one variable hardly changes between readings. If it seems that changes between readings are unexpectedly small, then this would be a reason to modify the plan. Analysis. There are 4 marks for the graph, and candidates are expected to be able to plot very good graphs at this level, so the criteria are applied quite strictly. At this level, the experiment will have a non-linear relationship between the variables, and so a log graph is often required, and the label for the log of a potential difference V, measured in volts, is shown on the A1 line. Appropriate scales means that the plots should cover at least half of both axes and should be multiples of 2, 5, or 10, so that interpolations and gradient calculations are easily made. Plots should be accurate to 1 millimeter, and if the line of best fit should be a curve, then candidates should draw a curve and measure the gradient of a tangent or the straightest part. Similarly, there are 4 marks, A5 to 8, for using the graph, and here, for example, a negative gradient should have a negative sign, but the constant will probably be positive. The gradient should be calculated from a large triangle, and appropriate units, that is, those from the graph, should be used subsequently. It is expected for A6 that the data used to plot the graph will be shown in one of the results tables. For A9, it is expected that the results table will show the numbers shown on the instrument, and that 3 significant figures will be used in all graph work, plotting and gradient calculations. If a reading on a micrometer or voltmeter goes over 1, say, so that adjacent readings are 0.95 and 1.07, then 2 and 3 significant figures are appropriate because this is what was shown on the measuring device. In an experiment on an oscillating system recording 10t to 2 decimal places, say 13.47 seconds will give a value for t of 1.347 seconds. The same number of significant figures. So recording 10t enables the results for t to be more precise than the measuring device. Furthermore, t squared can be quoted to 4 significant figures. We expect some reference to physics theory in the report. This can be mathematical, deriving the log equation, for example, or can be gained by referring to the basic physics ideas. A11 is for using the words precision and accurately, correctly, somewhere in the report. A12 should report on the sources of uncertainty found while doing the experiment. This is not the precision of an instrument and should be more than was said for P13. So A12 draws on the experience of doing the work to reflect on what was difficult to measure or likely to have a large uncertainty, whereas P13 looked forward to the work. A13 is for finding the percentage uncertainty in the variables by using the spread in repeated readings. A14 is for combining these to estimate the uncertainty in the final value or relationship mentioned in the briefing. Having estimated the uncertainty in readings, error boxes can be plotted and other lines of best fit drawn to pass through the error boxes, steeper and less steep, so that an uncertainty in the gradient can be estimated, leading to an uncertainty in the final value. A13 and 14 are for using the readings to estimate the uncertainty in the outcome and not basing this on the precision of the instruments. A15 is for suggesting changes to the methodology that will improve accuracy and reduce uncertainty, and these suggestions should be based on the experience of doing the experiment. For oscillating systems, it is unlikely that a light gate will help, because most software will only record a half a cycle in between adjacent passes, and this is a small time interval. A16 is for stating a conclusion based on the briefing and should be in the final part of the report. A17 is for using the data to qualify the conclusion, so mention of uncertainty is a significant help. A18 is for suggesting work that will develop the scope of the briefing, not for changing the values of the variables. And some physics is expected here too. The suggested practical work should be suitable for a well-equipped A-level laboratory. There is further help with criteria in the document entitled Notes on Assessment Criteria available on the website. We will now see how the criteria are used in practice. But first, we look at the suggested practical tasks that are detailed in the document Assessments for Unit 6. To access this document and others that have the padlock icon, you will need to contact the examinations officer for your centre and obtain a login to access confidential materials such as these from the website. Please remember that this document should not be shown to your students as it contains briefing sheets for all the practicals and exemplar plans. Whichever briefing and plan the candidates use, the briefing and plan should form part of the candidate's work and should be submitted together with their written material at the end of the assessment. Crossing the tracks sets the discharge of a capacitor in the context of a time delay circuit for a level crossing, and candidates have to verify a relationship and select components to satisfy a design brief. The damped pendulum is about a decaying oscillation and aims to determine the damping constant. A diode thermometer is about the temperature variation of the forward bias current in a diode, and although this sounds complex, it is very straightforward to carry out and produces an excellent estimate of the charge on an electron. Mass in space measures the period of an oscillating spring as the suspended mass varies and seeks to determine the mass of an object. This is very good for using uncertainties to justify a conclusion. Low-energy light bulbs uses an LDR to investigate the energy dissipation by two different light bulbs and is an inverse square law practical. You should notice that all these practicals require little apparatus and so are cheap to set up, even for a large number of candidates, and certainly use apparatus that is readily available in centres. All are based on physics that is on the specification, and they involve variables that have a non-linear relationship. They also have a definite outcome that enables the candidates to draw definite conclusions from their data and hence, overall, enable the candidates to access all the criteria. Although you will use only one for the assessment, others can be used as rehearsal. Should you choose to use a briefing of your own, it should fulfill all the constraints just discussed. Tracks, pendulum and mass in space are the popular ones. There is also available on the website under Tutor Support Materials a booklet entitled Guidance for the A2 Practical Assessment, and this contains further practicals and a wealth of further detail about the assessment. Usually, candidates carry out their own plan, but you can give them one from the booklet having collected in their own plan which will be needed for marking. We will now look at a real marked script. When using real scripts, we remove everything that might identify the candidate or the centre. This script is at the E boundary and scored a total of 22 marks, which means it's just below an E grade. In what follows, it will help if you have the list of criteria to hand, as we will be using the mark codes to identify where the marks have been awarded. The practical used here is measuring mass in space and concerns the calibration of an oscillating system that is then used to measure an unknown mass. As we go through, you will see no evidence of the marking from the original examiner. As this is a 1A script, it was moderated by an edXL moderator, and so the script has not been annotated. It is unusual that it shows no signs of marking by the centre. We do ask that when marked by the centre, the script is annotated to assist the process of moderation. This is a good and clear diagram that shows the ruler close to the spring. The equipment list lacks detail, but as the masses are labelled in the diagram, it is worth P1. The precision, misspelled, is 1 millimetre, not 1 centimetre, but that does not concern us here. This diagram adds nothing to the first, and it is not necessary to draw a stopwatch. It would be helpful if there was a fiducial marker shown, but the candidate scored P3 with the first diagram. This list does not really add anything. We need more information about the masses, and perhaps the spring to score P2. The ruler should probably have divisions of 1 millimetre, but it will be used to measure the extension, and an estimate of the percentage uncertainty is given to score P4 and P5. We do not award any further marks for the extension experiment, as it is not really an A-level experiment, but it will provide data for later comparison. We do this to bring this practical in line with the others, which have only one opportunity to score the marks. The experiment is to determine a value for K. This candidate selects an appropriate graph to plot, but does not say how they will determine K. They do not score P12. The candidate chooses to measure 10T and gives a reason, so scores P8, and carries on to score P6 and P7 with an estimate of the percentage uncertainty in using the stop clock, even if it is a little pessimistic. The misspelled fiducial marker would be of use in the second experiment rather than the first, and the human timing error needs more detail for P13. School labs are indeed usually very safe places, but the candidate manages to find a hazard and a precautionary G-clamp. The plan did not mention controls or repeats, and the spelling of the technical terms was poor, so P9, 10 and 14 are not awarded, and neither is P16. The candidate does not give any detail of what will take place. P15 is awarded to give a score of 9 out of 16 for the planning section. This table is shown for completeness. We do not mark the force extension one, again so that all the practicals have the same opportunities to score marks. The mass is recorded to the nearest 10 grams, which is not the very small error discussed earlier, and the uncertainty in time is not mentioned either. So M1 and M2 are not scored. M3 is OK because we only look at measured or variable quantities and not derived values. Here, kilogram and seconds are fine. There are sufficient readings to plot a graph, and the value of T doubles over the range, so we award M5 and M6. While 10T is recorded to 3 significant figures, the value for the mean T should be as well. It is not decimal places that matter here, so A9 cannot be awarded. The force extension graph is shown for completeness, but will not score marks. It is a good graph showing that a force is needed to start extending the spring. The calibration graph has been compressed and distorted in order to fit it onto the slide, and unfortunately the grid lines have not been copied. Nevertheless, all the marking features are shown. A1 is not awarded because of the unit of T squared. The scales stretch out the plots across the page and have sensible divisions. The 2 plots checked are correct, but the line of best fit has been forced through the origin, so A4 is not awarded. As T squared was tabulated, we can award A6. The gradient measures and calculation are correct for A7, and K is calculated correctly and shown with units. Ignore the typo here and look at the next page for the unit properly expressed. So A5 and A8 are awarded. M4 is awarded for the discussion about the 50-gram reading. So now we have a total of 4 for the I and M section. Notice the gradient values. The method of using wayward plots to determine uncertainty is unconvincing if for no other reason than it seems to give rather large uncertainties, as the 15% here. Look back at the graph on slide 23. A lot of plots lie on the line of best fit. The errors in both variables are discussed for A12, and percentage uncertainties are calculated, but the compounding of uncertainties is based really on one reading, and so A14 is not awarded, but A12 and A13 both are. A pointer is meant here rather than a fiducial marker, but there is little that will improve the work. Valid reasons are given to support the outcome, so A16 is awarded. But we expect some numerical support in this practical for A17. Horizontal springs are mentioned in the briefing, so some development of this idea is needed for A18, and there is not enough here. This gives the candidate 9 out of 18 for the analysis section, and a total of 9 plus 4 plus 9 for 22 out of 40. We now turn to a rather more successful script. This script scored 33 and was awarded an A grade. It is a 1B script, and so the centre submitted it for marking by an Edexcel examiner. The annotation of the script is the examiner's marking. The script was also used for monitoring, and a senior examiner also marked it, which is why there are 2 sets of annotation. This is a process that helps to achieve an equal standard for all scripts. The experiment performed here is crossing the tracks, where a charged capacitor discharges through a resistor. The voltage across the resistor is measured as it falls. There is also a design aspect to the work. The first page shows some preparatory work to determine the values to be used in the practical. There is enough here to merit the award of A10. Any of the marks can be awarded, if appropriate, in the planning section, but planning marks cannot be awarded after the end of the planning section. The examiner writes "seen" on the page to indicate that it has been read, otherwise there is no annotation. This page shows the fruits of the work done on the first page, enabling the candidate to be quite specific about the apparatus. They score P1, 2 and 3 here. P4 is an easy mark, and P5 could be awarded twice, either for the percentage uncertainty based on the precision of the instrument, or for pointing out that a human operator has slower responses than the precision of the watch. So, it is a suitable instrument for this practical. This shows a good explanation for P6 and P7. Numerical support for the choice. This is a good technique in what can be quite a pressured activity, and scores P8. It also shows a good way of ensuring that each run starts exactly the same way, so P9 too. Reversing the polarity of the capacitor can have dreadful effects, so this is a safety matter. Dealing with mains electricity is a routine affair, but worth mentioning sometimes. Repeat readings are discussed, and a full-scale repeat is necessary to check readings. Even more important, then, that the starting point is the same. The readings are then shown to produce the desired outcome, thus scoring P10 and P12. Reaction time is mentioned, but without reference to its effect. But the simultaneous readings are significant, so A13 is scored, and as the plan is clear and the spelling accurate, with at least 3 headings, the total is 16 out of 16 for the planning. In the plan, the precision of the voltmeter was given as 0.1 V. As this cannot be checked, we would allow M1 here if it were not for the time. The precision of the clock is 0.01 seconds, and reaction time is 0.2 seconds at most, and probably variable. We expect the time to be recorded to 0.01 seconds, which is what it says on the screen. M1 is not awarded. The units of the measured quantities are right, and there is an uncertainty shown for both of them. A good number of readings over a range that shows the potential difference to halve. M2, 3, 5, and 6 are awarded here. M4 is scored by discussing the arrangements to obtain the right resistor value. M4 is scored for a total of 5 out of 6 on this section. The graph has been truncated to fit it onto the slide. The log unit is correct, and this graph scores all 4 graph marks, as well as A6 for tabulating the data. A line of best fit is drawn, and 2 other lines, steeper and less steep, are drawn to give an uncertainty calculation. But for A7, we expect the line of best fit, for the plots themselves, to be used to calculate a value for the gradient and not to rely on the average of the 2 values for the other lines of fit. A4 is awarded with the benefit of the doubt, as the data might also fit a curve. The discussion of the effect of simultaneous readings is very clear and well worth A12. The issue of the disparity between the expected and the actual readings is also addressed, along with the notion of contact resistance. The numerical treatment of uncertainties is not so successful, because the precision of the voltmeter is used rather than the spread of repeated readings for calculating the uncertainty. The derivation of the log version of the equation completes the evidence for A10. The other lines of fit are used for an uncertainty in the gradient, although only 2 significant figures are used. This slide shows a mixture of significant figures, and so A14 is awarded for the uncertainty, but not A9, which was lost earlier anyway. This does not mention the problem of the simultaneous readings. Neither does it say what sensors will be used. Not A15. The conclusion is good for A16. and well supported numerically for A17, but they lose A8 here for missing units. The further work contains a good idea, but lacks practical detail. Not scoring A18, and so achieving 12 out of 18 for the analysis, and 33 out of 40 overall. That completes the course for today, but you can access the presentation at any time to have another look at some of the large number of details that we have covered today. On the screen is a summary of the help that is available from the website. And here is some of the more direct help available. Thank you for using this course, and good luck with your assessment.